Last skill here with kinetics, and I know this learning unit has been really challenging. It is intense. It is intense. So we're going to try to do a lot to kind of practice things to kind of help you guys feel comfortable. So last skill really is kind of a couple of things together. It's not really a single skill, but it's sort of the last piece that we have here. And it's on thinking about reaction coordinates and then reaction mechanisms. Okay, so first piece here is just kind of learning how to use an equation that looks similar to some things that we've talked about before. At the very beginning, when we talked about sort of kinetics, I mentioned that there is a temperature dependence on rate and rate constants. So if we think about this, this makes sense, right? If you want to make a reaction go faster, often you heat it, right? That's how we make things cook faster. Or in a refrigerator, we slow down kind of chemical and enzymatic processes by lowering the temperature. So there's definitely an effect of temperature on rate and rate constants. So here's an equation. Again, you just need to know how to use it and when to use it. It's called the Arrhenius equation, and it's a useful equation that when we want to figure out something called activation energy. We'll get to what that is in a minute, but it basically allows us to measure rate constants for a process at two different temperatures, and then we can use this equation, right, to solve for activation energy. So you've seen an equation like this before. In Unit 1, we saw the Clausius-Clapeyron equation. Very similar here. We look at the temperature dependence of pressure on gases as a way to determine the enthalpy of vaporization. So remember, these equations really just represent something that has 5 different variables, 2 temperatures, 2 rate constants, and then usually what you're solving for is the activation energy. So you just need to know how to solve these equations for the unknown that's being asked. Okay, so we'll practice a problem like that in class. Another skill that's important is learning how to draw reaction energy diagrams, sometimes called reaction coordinates. And it basically is a plot that shows how energy changes as the reaction proceeds. Okay, so it allows us to think about those energy changes. So reaction progress is plotted on the x-axis, and then energy is plotted on the y-axis. And what we really see is what we call an energy landscape that shows how as we go from reactants to products, in this case we start out at low energy, we go through an energy barrier, we'll talk about that in a minute, and end up in species that are higher in energy. We can also have a reaction that goes downhill where the reactants are lower in energy. Okay, so one of the skills is learning how to draw an energy diagram. So I'm going to go through that with you here. So drawing an energy diagram, we're first going to start out by drawing axes here. Okay, you're going to label your x-axis reaction progress, and you're going to label your y-axis energy. So there's lots of different ways we can measure energy in chemistry. We've learned about enthalpy already, so this might be the letter H for enthalpy. Okay, we're going to learn other ways that we can think about energy later on. So whether you label it energy or the problem talks about enthalpy, both of them are going to be totally acceptable here. Now we need to label, add in and label energy levels for reactants and products. So I'm going to draw here a reaction that goes downhill in energy, meaning that my products are lower in energy than my reactants. Okay? Okay. If I had something like I had over here where my products were higher in energy than my reactants, we'd call that an uphill reaction. Okay, so this one I've got a downhill reaction, and now I'm going to draw a hill that starts at reactants that goes up and over to products. So this is the key here. I'm going to go up and then over to products. So this is how you draw an energy diagram. Now sometimes we might be given some information that gives us some values that relate the difference in energy levels between reactants and products or to the height of our peak up here. We're going to label these on our next slide here. So let me go ahead just so that I have an easy way. I'm going to copy and paste this so that we can go on to the next slide to talk about, well, what are the things that you might label on an energy diagram here. So I'm going to put this guy in here. So we're going to label relevant species here. So delta H or that difference in energy, is the difference between reactants and products. So this energy difference here is delta H, okay? In this case, delta H is going to be negative. Remember, anytime we have a delta, it's going to be the energy of our final products minus the energy of our initial. We've got a smaller number subtracting a larger number, so that's why that's negative. And this negative is also indicative of this going downhill. All right, transition state. Transition state is right there. That's just the peak that we go through. Activation energy is the height of the hill. Okay, it's actually drawn from the energy level of the reactants up to the transition state, and this is going to be the activation energy for the forward process. Look here, I can actually draw an activation energy going in the reverse direction. So these activation energies are always drawn from a species that's kind of in a valley, if you will, up to a peak. That's one of those transition states. And so if we wanted to talk about going in the reverse direction from products to reactants, that would have that blue activation energy. So as you have problems that you have to draw with these, try your best to draw them to scale. So they might be giving you values for the delta H and the activation energy parameters, so try your best to draw them so that they're relatively to scale. Last thing is to learn how a catalyst speeds up a reaction. So let's draw this in purple here. If we're going to have a catalyst here, catalyst speeds up a reaction by making a smaller hill to go through. So what I'm really going to have here is I'm going to have a smaller hill to go through. So this is going to be a catalyzed reaction. Okay, so what that means is my activation energy is smaller. So this is my activation energy for a catalyzed process. We've lowered the transition state. So this is my transition state for a catalyzed process. Okay, so I've lowered that peak, and by doing so, I've lowered the activation energy. We'll explore this concept a bit more later on, but make sure to note here, I haven't changed the energy level of my reactants or my products. I've just lowered the energy of my hill, which allows me to have a smaller activation energy that I need to put in to go from reactants to products. Okay, so that's how you draw a reaction energy diagram. The last little piece in this sort of grab bag of things in our last skill is thinking about reaction mechanisms. Okay, so most reactions actually occur through what we call a reaction mechanism. So let's say we had two A's plus B making an E plus an F. Well, in reality, this is not necessarily the single thing that happens. Okay, these above reactions might involve some simpler steps. Think of this like Hess's law when we'd have individual reactions that we added up. So maybe the first step is an A reacting with one B to give us a C molecule. Okay, then C might react with the other A to give us the D, and then the D actually undergoes a decomposition to give us the E plus the F. Okay. Some important kind of pieces to highlight with what's going on here. C and D are what we call intermediates. These are products that are generated in one reaction, okay, but used as reactants in a subsequent reaction, such that when we sum everything up, intermediates never appear in the overall reaction. Okay, so that's an important distinction of what an intermediate is compared to a reactant or a product. The other thing I want to highlight here is these two processes are what we call bimolecular. Bimolecular meaning we have two molecules, an A and a B in this case, a C and an A in this case, reacting to form product. Okay? This last reaction is what we call unimolecular. Only one reactant undergoing chemistry to generate a product, or in this case, two products. We want to be able to identify the molecularity of these reactions because that's going to be an important step in doing this last skill here. So what is this last skill? Well, chemists like to do things like propose a mechanism for a reaction. Okay? Then they perform a test to see if their mechanism kind of satisfies the rules And one of them is kind of seeing if it matches the observed rate law. So we've got a list of 3 steps, a checklist of 3 things that we need to go through to see if our reaction mechanism passes. Okay, so stay with me here. One other thing to talk about. Remember when we were doing our rate law stuff and I told you don't ever take coefficients from a balanced chemical equation and make them exponents in a rate law? Well, I knew this was coming here, but when we are doing this thing with reaction mechanisms and we have these single reactions that we call, these simpler steps that we call elementary reactions, if you know that it is an elementary reaction or an elementary step, then the coefficients can become exponents in your rate law. For example, looking at this guy, the rate law would be rate equals rate constant times the concentration of A to the first power times B to the first power, because it's first order with both of these because that's what the coefficients are. Let's take another sort of hypothetical reaction. If 2 Y's interacted to form Z, well, then we could write the rate law as rate equals rate constant times the concentration of Y squared. Because we know that this is an elementary reaction, we can take the coefficient and have it become an exponent. But the only time that you can do this is if you know that that reaction is an elementary reaction. Okay, so let's get to our checklist of 3 things to tell whether a mechanism is valid. All right? So validating a reaction mechanism means we need to go through this 3-part checklist. If all of our pieces check out, then the mechanism is valid. So 3 questions you need to ask. You're never going to have to propose a mechanism or do anything. You're going to be given all the pieces and then you have to answer the question, is this valid? You need to make sure that all of the elementary steps sum up to the overall equation. If they don't, then you fail right there and the mechanism cannot be valid. So this is like Hess's law. You have to add up all of those elementary steps and make sure that they sum up to the overall equation. If they don't, you fail that first step and your mechanism cannot be valid. Second step is ask, do I have reasonable elementary steps? If they are not uni and bimolecular, for example, if they had 3 things that were trying to interact, you have failed the second step. Cannot be a valid mechanism. So make sure that no more than 2 species are listed as reactants. Otherwise, it's going to be more than a uni or a bimolecular reaction. Last piece is you have to make sure that the mechanism that you're proposing must correlate with the experimental rate law. All right, so what does that really mean? One of the steps is going to be listed as a slow step, okay? Because these are elementary reactions, write the rate law for that slow step, and as long as it matches the experimental rate law, you're good to go and that mechanism is valid. All right, so let's practice that with a real problem here. Here is the overall chemical reaction that we're looking for or looking at, and here is a proposed mechanism. We've got a slow step and then a fast step. So let's see if we can see what's going on here. In the slow step, we've got 2 NO2 molecules that are reacting to generate NO3 and NO. In our second step here, we're going to have NO3, which I'm going to box this here. This is an intermediate. Do you see how it appears as a product of the first step and then as a reactant in the second step? Okay, so that's an intermediate. So now we're going to have NO3 reacting with CO to generate an NO2 molecule and CO2. So the first step is let's see if our overall reaction can be created by summing up these elementary steps. All right, so I've got on the left-hand side, I've got 2 NO2s, but look, I've got an NO2 on the right, so those are going to cancel out. My intermediate is going to cancel out, so I am left with an NO2 plus a CO, which is what I have here. And then I'm going to have an NO and a CO2, which is what I have here. So I've passed my first step. Okay, my elementary reactions sum up to my overall. Second piece is just look at your elementary reactions. Make sure that they don't have a lot of stuff as reactants. Well, my slow step, my first step there, is listed as a bimolecular reaction, and so is my second step. So they're both Okay, they're both bimolecular. Now, the last thing is make sure that the rate law for the slow step matches the experimental rate law. So let's go ahead and write what the rate law is for our slow step. Remember, if it's an elementary reaction, I can write the rate law using the coefficients. So the rate law is going to be equal to the rate constant times the concentration of NO2 raised to a power that is the coefficient from the balanced chemical equation. Note here that this was really 2 NO2s makes NO3 plus NO. Okay, so the fact that there's 2 of these, there was that coefficient of 2, means that I have that coefficient. So that is the rate law for the slow step, and here's the experimentally observed rate law. These two match one another, and because they match, I get my third check mark there, and this reaction mechanism is valid. Okay, so lots of ways that I could invalidate this reaction mechanism. Maybe I could have something going on where these reactions didn't sum up to this. Maybe I could have where one of my reactions had 3 pieces on the left side. But the easiest way to kind of write a reaction mechanism that wouldn't be valid is if I tried to make this guy be the slow step, right? Making that guy be the slow step is going to be complicated, but it's also not going to match my slow step being what I observed experimentally. Okay, so we're not going to do a ton with this kind of chemistry, okay, but I do want you to know the different steps that you need to have to validate a proposed mechanism.